Assembling your own circuit boards is hard. All the components are so small and wait, this can't be right. These components are massive. This is the size of components that I normally use compared to a grain of rice. No, not here. Here. These are called 0201s, and they're 0.6 by 0.3 millimeters, which makes them a nightmare to hand assemble. These ICs here are not much better as their pins are tiny and very close together. One small misalignment can cause a catastrophic failure, so factories use million-dollar machinery to achieve the most cutting-edge precision. But can I prove that the highest precision can be achieved with the lowest possible price? This is the story of the pick-and-place machine. So the premise is quite simple. To assemble the board, all we need is a picking tool, and a way to move it in 3D space and rotate it. That sounds easy, right? So to challenge myself, I will be constraining myself to a budget of $2,000.
No one can afford that.
A budget of $200. Anyways, around a year ago, I built one of these pick-and-place machines, but I haven't used it in about a year. The issue was simply a lack of precision. While the design was quite smart, it was quite flimsy and could only assemble 0603 components, or 0402s at best, which I can already reliably assemble myself, 10 times faster. This pick-and-place machine is also manual rather than being automatic. I actually prefer this for personal use, as you don't need to rely on external software to generate movement commands, you don't need a camera to scan the components, you don't need an automated component reel, you don't need to worry about PCB alignment, the PCB doesn't need to be held in place with any kind of fixture, this will work on PCBs that don't have design files available, and the simplicity makes the machine so much easier to use. The only disadvantage is that the assembly speed is quite slow, so it won't be suitable for large-scale production. So let's say we have a gantry that can move a tool head in 2D space. How would we motorize this? Motors have rotational movement, which we somehow have to make linear. The simplest approach is a rack and pinion. However, this has backlash and the step size is too big. Another idea would be a belt, but again the step size is relatively large, which is great for high speeds, but doesn't work too well for micro movements. Instead, speed can be traded with precision using lead screws. These are the most common ones that you'd find in the Z-axis of a 3D printer. In fact, all of my 3D printers have these. These most commonly have 4 threads with a pitch of 8mm. So when the motor makes a full turn, the linear equivalent would be 8mm. With 200 steps in a turn, that makes the linear equivalent of 0.04mm per step. But wait, haven't you seen the threads of screws? These have a pitch far smaller than these lead screws, with M3 just having 0.5mm of linear movement per turn. If we slap an M3 rod on a motor, we can get 2.5 microns of movement per step. But let's compensate for any mechanical inaccuracies, and let's reduce this by a factor of 4 to get a safe estimate of 10 microns of precision, which even then is about the length of a human blood cell. Backlash can also be reduced by the screw using 2 nuts, which are in slight compression against each other. Right, so in my first pick-and-place machine, I had a series of buttons to control the movement of the toolhead, which did work, but it was a bit clunky. So in this version, I'm reducing all of this down to just 2 joysticks to control the 4 axes of movement, X, Y, Z, and R. The components will be picked up with a vacuum, which will be toggled by pressing down on the joystick, and I have hired a professional artist to demonstrate how each joystick works. Let me just do this myself. So basically the motors will spin slowly when the joystick is moved a little, and they'll spin fast when the joystick is moved all the way up and down to the edge of the joystick. And each joystick will control 2 motors, one for X, Y, and the other for Z and R. Now my original reasoning for wanting joysticks is because I wanted to go for a full analog approach. Let's break it down. Let's break it down. Let's say we have one potentiometer and one motor, and we want to control the motor's speed. The potentiometer outputs a voltage of 0 to 5 volts depending on its position, with 2.5 volts being in the middle. The stepper motor uses a driver which works on essentially 2 pins, step and direction, often simplified to DIR. These are extremely simple. DIR controls direction. When high, the motor spins one way, let's say clockwise, and when low, it spins the other way. The step pin increments the motor's rotation by 1.8 degrees with every pulse, so more frequent pulses result in faster rotations. We also want to have a dead zone in the middle, because joysticks are never exactly 2.5 volts in the middle, and even 2.501 volts will make the motors drift ever so slightly. And you know, we want the motors to not spin when the joysticks aren't being touched. Anyways, as the joystick is moved more up or more down, we want the motor to accelerate. When the joystick is near the middle, the motor should spin slowly, and when the joystick is pushed to its extremes, we want the motor to spin as fast as possible. So the direction change is quite simple. The output of a potentiometer can be compared to a known 2.5 volt reference, which will output a high or low signal if it's above or below this threshold. The dead zone can be implemented with a stepper motor's enable pin and 2 comparators. These comparators check if it's above 2.4 volts and below 2.6 volts. An AND gate can be used when both comparators are satisfied, sending a high signal to the stepper motor's enable pin. This, well, disables it. The step pin, on the other hand, is a bit harder. We first need to take the input voltage and remap it. We need to have 5 volts in the middle and 0 volts in each of the limits. However, the stepper motor driver can't interpret this analog voltage, so we need to turn this voltage into a square wave. And this could be done with a simple NE555 chip, in a configuration like this to make a voltage controlled oscillator. I just needed to figure out how to get this voltage remapper to work. I've tried everything, but the only way I can make this work is with a microcontroller. And you know what, if we're using a microcontroller, screw it, why not make the whole thing digital anyways? I'm sure it'll be cheaper. I designed this PCB around the Arduino Nano, which should be able to control everything. Technically, it's not an Arduino but an ESP32 dev board, built around the same footprint as an Arduino Nano. I used this ESP chip to squeeze out as much performance as I could get for those high frequency pulses. So completely unrelated to this project, I disassembled an old Ultimaker 3D printer, and would you look at that, the mainboard has 5 stepper motor drivers, plenty of ports, uses the ATmega 2560, is fully open source, and has broken out header pins which aren't connected to anything in the design. Christmas has come early. But anyways, this mainboard is absolutely perfect for what we need, so I slapped on some code and I got this working great. Although these motors and mainboard were free, I'll add the cost of these parts to the running total. All I had to do next was CAD up a machine. To prioritize cost, all of this is built with 2020 aluminum extrusion, linear guide rails, and some 3D printed components. All of this totaled to just under $180, which will be around $190 or $195 when you account for all the 3D printed plastic. Some of these parts will be printed with FDM, while the others will be printed with resin for maximum precision. These gears were printed with absolutely zero clearance, and when spun against each other they would bind. But this wasn't by accident, this was on purpose. After adding some abrasive compound and spinning these together for a few minutes, the surfaces would be worn down just enough to be an absolutely perfect match. Since these are also herringbone gears, the point of contact slide up and down the gears during rotation. This removes any micro disturbances which you'll get from regular gears. After quick clean and lubrication with some silicone spray, these spin unfathomably well. It's hard to get this across on camera, but the buttery smooth meshing is probably some of my best work up to date. That's it, the Magmabow company has peaked. Anyways, the point of these gears is to lift up and down 2 pick-and-place tool heads, one of which has a small nozzle for 0201 components and 0402s, and the second one has a bigger nozzle for 0603s and up, as well as ICs like this. So you know what, let's build this thing. I ordered these PCBs from PCBway, and of course they're just flawless yet again. I know these boards are simple, but it's all we really need. If you want to order your own PCBs, just go to PCBway, drag over your Gerber files, and place the order. You can get 10 2-layer PCBs for just $5. So, there are a few issues. First of all, a couple of the resin prints don't fit on the extrusions because some genius forgot about clearances. The second issue is that these PCBs have the wrong footprint. In my defense, the joystick image on my supplier's website looks identical to the ones I'm using, just scaled down for whatever reason. The third problem is that these vacuum pumps aren't vacuums. Instead, they blow air out, regardless of polarity. Anyways, I printed off some new components from ASA, ordered new vacuums, and PCBway kindly manufactured new boards for me. Here I swapped over 2 of the joysticks so my right hand controls the toolhead, and my left hand controls the gantry. I felt this configuration would be more intuitive to use, and by the way, you can always 3D print a PCB to test component fit. Just make sure to expand the hole slightly so the pins fit. So we might have another problem. The motor that lifts the nozzles keeps skipping as it's too weak to fight gravity. My first idea was to use a spring in a configuration like this, but this range of motion wasn't big enough, and the vertical force was not constant. Also, this can't be good. Springs have a force proportional to their extension, so to reduce the difference in force we can use a longer spring. So the overall percent change in extension means a small percent change in force, and this makes the force closer to being constant. So then I designed this side mount, which works fairly well, is adjustable, and doesn't look too out of place. Now all the problems are solved and it should be smooth sailing from here. What? Okay, fine, there may be another issue. So we have 5 stepper motor drivers here, and 6 motors. No problem though, we can use this stepper motor driver and connect some spare GPIOs from this header down here, and now it works perfectly. Man, after hitting my head against the wall for a bit and some bodged wires, I finally got it working. Oh my god, this stepper motor driver is so damn unreliable. It keeps just dying. I don't even know why. It makes no sense. Like, electrically it's all fine, all the signals are okay, it's not shorting anything, and it just randomly overheats and stops working. I mean, I guess we technically don't need it, the machine works without it, and we don't really need 2 motors with X-axis. 1 will probably do. Oh well. Now, because my first PNP machine got a montage, I think this one deserves one too. Look at this statistic, 95% of you are not subscribed. Damn, that's embarrassing. You guys should get subscribing. Anyways, here's the montage. So this control panel is actually detachable, and it snaps into place with some magnets. And here is the motion of the gantry, and the tool head. It's not the fastest, at all, but for what it lacks in speed, it makes up in precision and accuracy. Okay, wow, this machine is very slow. I'm gonna have to make this faster in software. To test this machine, I have this unpopulated PCB, again ordered from PCBWay, and this assortment of tiny components, including 0201s, 0402s, and even this big chip. So I only have one of these chips, so we only have one shot of doing this. So who is this machine actually for? I'd say professional hobbyists. This bridges the gap between hand assembly and fully autonomous production. The point of this is to make precision PCBs more accessible to the layperson at low cost. In an ideal world, I see this machine being on the benchtop of every electronics maker, and I will become a millionaire kingpin who sells the shovels in a gold rush. However, this machine is not for sale, but it's completely free and open source. Because of that, I don't make any profit. This is a one-person channel, fully created as a passion project, often at a loss, even with sponsorships. All I ask for is a subscription and a like on this video. It really is the best way of supporting the channel. Editor here. See this number? Remember it, as it's gonna be important later. Ah, shit, the components floated away. Ah. So, I may have burnt the ever-living shit out of this board. The soldering temperature for these boards should be 240 degrees, but I may have set it 100 degrees too high. You know, at least all the components are on pretty nicely, so I guess that means the machine did a good job. So thank you for watching, and make sure to check out the project on printables where the design files are provided. Also check out PCBWay's capabilities through the link in the description. A lot of resin parts for this project were actually manufactured by PCBWay. They are reliable and their quality is honestly fantastic. All of these parts were pretty much flawless. Anyways, thanks again for watching, and I will see you guys next time.